Hi everyone and welcome. In this video we will learn about least upper bounds and greatest lower bounds. These are two very important ideas in real analysis that will actually lead us very nicely to the axiom of completeness, which is the thing that distinguishes the set of real numbers from the set of rational numbers. We will begin this video in somewhat familiar territory, which is the maximum and the minimum of a set. So you probably have some intuitive idea of what the maximum or minimum of a set might refer to, which is the largest and smallest elements of a set, and you would be right. But let's see how we can capture that mathematically. So the definition of a maximum is that the maximum of a set A is denoted by the maximum of A, and it's a real number satisfying the following two conditions. First of all, the maximum of A should actually be a member of the set A. And number two, the maximum of A should be bigger than or equal to everything inside of A. And similarly, the minimum of a set A is denoted by the minimum of A. And it's a real number satisfying the following two properties. First of all, the minimum of A should actually be a member of the set A itself. And number two, the minimum should be smaller than or equal to everything inside of A. So the key point to take away here is that the minimum and maximum, these must be members of the set A in question. Next, let's take a look at a few examples just to make sure we clearly understand what the maximum and the minimum of a set are. And we'll see that they're actually quite restrictive. As a first example, let's take A to be the finite set that has 1, 10, 100, and 1000. Then you can see the minimum of this set has to be the element 1 and the maximum of this set has to be the element 1000. Notice that they're both elements of the set, and moreover these are like the extremes, right? Like for example, the maximum is bigger than or equal to everything in this set. For the next example, let's consider the interval from 2 to infinity. Since we're including 2, it follows that the minimum of this is actually just 2, because 2 is a part of this set, and also 2 is smaller than or equal to everything in this set. But the maximum of this set does not exist, because this is an unbounded set and the numbers just keep increasing forever. There is no maximum. We will always be able to find numbers larger than whatever maximum we pick. Let's take a look at another example. This time we have the set of reciprocals. So we have 1 over 1, 1 over 2, 1 over 3, 1 over 4, and in general 1 over n for any n. And so what we can see is that the maximum of A in this case is 1. And then after that the numbers start decreasing. The minimum of this set does not exist because the numbers arbitrarily get closer and closer to 0 without actually reaching 0. So as a picture, if we draw a number line, here's 1, here's a half, here's a third, here's a fourth, here's a fifth, and we keep getting closer and closer and closer to 0, but we don't actually reach 0. And so 1 over n is always positive. Let's suppose there was a minimum of this set. Let's call it m. Well, then I can take 0 plus m divided by 2, basically m divided by 2, which is the midpoint, and that will be a number to the left of m, but still to the right of 0, right? And that would contradict that what I picked was actually indeed the minimum. So no matter what you pick as the minimum, I can always find numbers just to the left of it, but also to the right of 0 within the set. In the next example, let's consider the closed interval from 0 to 1. Then clearly the minimum is 0 and the maximum is 1. They're both elements of the set and they're both extrema of the set. Here's a similar example, but instead of the closed interval we have an open interval from 0 to 1. Then it turns out that the maximum and the minimum both cannot exist, because the numbers in this interval get arbitrarily close to 0 and 1, but don't actually reach 0 and 1. And so just for some practice, let's see how we can actually prove something like this rigorously. Suppose, for contradiction, that the maximum of the open interval from 0 to 1 exists. Then let's give it a shorter name, let's call it m. Then this m satisfies two conditions. The first one is that it must be actually an element of this interval. That is, m is a number between 0 and 1. And the second condition is that it should be greater than or equal to everything inside this interval from 0 to 1. Now the idea to get the contradiction is actually to construct a number that is actually larger than m but still inside of the set, and that would contradict the fact that m that we picked is the maximum. And the way we will do this is, let's consider the number line here. Here's the open interval from 0 to 1, And let's say I picked my maximum, right? I picked my maximum right over here. And well, you might say, well, you didn't pick the right maximum because there's still space left. And yeah, you're right, we can still move the maximum more and more to the right here, but then I can zoom in on that and it will look like this. The whole idea here is that no matter how close you pick M to this right endpoint, if you zoom in far enough, you'll still see empty space. And so to construct a new element that is larger than M, but still within this open interval, let's consider the midpoint of M and 1, or the average of M and 1, which is simply M plus 1 divided by 2. Let's call this number X. And now let's rigorously show that this element X is an element of the open interval from 0 to 1, and moreover, it's strictly larger than our maximum. Okay, so this might be an overkill for this question, but let's just get some practice on how you do stuff like this. So let's begin by showing that X is actually between 0 and 1. So what I want to show is that M plus 1 divided by 2 is strictly less than 1. Well, notice if I multiply both sides by 2, I get this inequality, and then if I subtract 1 on both sides, I get this inequality, and this is clearly true. M is strictly less than 1 is obviously true because M lies in 0 to 1. But the way we write the proof is in the other way. You notice how in the proof I started with M is less than 1, something I know, and then I derived the conclusion that it must follow that X is less than 1. Similarly, we can prove that X is actually greater than 0. And so what I want to show is that M plus 1 divided by 2, this quantity is strictly positive. And so if I multiply both sides by 2, I get this inequality, and then if I subtract 1 on both sides, I get this inequality, that M is strictly bigger than negative 1. And this is true because M is greater than 0. Well, if M is greater than 0, then obviously it's bigger than negative 1. And so in the formal proof, I start here. I start with what I know is true. I know that M is bigger than negative 1, and then I can work my way backwards to show that it must follow that X is bigger than 0. So if you're already familiar with proofs, then what I've done here of starting with the conclusion, working my way backwards, and then in the proof, writing it in reverse order, should be quite familiar. But I just wanted to add this little detail in for those viewers that are not as familiar with proofs. But the general guideline when you're writing a proof is you want to do some exploration work on the side, some scratch work, where you start with what you want to show, which are these conditions, and then you manipulate and work with these equations to get something that is obviously true. And then in the proof, you actually start with what's obviously true and write the proof in the opposite direction. But anyways, what we see is that the element X here that we constructed does indeed lie in the open interval from 0 to 1. And now let's show that this element X is actually larger than M, strictly larger than M. So what I want to show is M plus 1 divided by 2 is strictly larger than M. And so if I multiply both sides by 2, I get this inequality. And then if I subtract M on both sides, I get M is less than 1. And again, this is something that is obviously true or is known in this proof, that M is strictly less than 1. And so in the formal proof, I've written it the other way. M is less than 1 implies this, which implies that M is strictly less than X. And so now we're done because we have a contradiction. We supposed that there exists a maximum for this set, but we were able to construct an element of the set strictly larger than the maximum. And so therefore, the maximum cannot exist. And that completes the proof that the maximum of the open interval of 0 to 1 cannot exist. At this point, I would highly encourage you to pause the video and try a similar proof for the minimum of A, as getting comfortable with proofs like this is very important in real analysis. You will find yourself trying to write out proofs like this quite often. And lastly, I would like to point out an important thing about maximum and minimums, which is how restrictive they are. If we consider, for example, the interval from 2 to infinity, and this example where we have the interval from 0 to 1, you can see in both cases the maximum do not exist. But in the first example, it sort of makes sense why the maximum does not exist. It's because it's an unbounded set. The elements of this set keep increasing and increasing without bound, so there's no way there could be an upper limit. But in the second example, the open interval from 0 to 1, this is a bounded set, right? It sort of feels like, intuitively, it feels like there should be some upper limit. Even though the maximum does not exist, we should still be able to say that there is some upper limit to this set. And so what we want to explore next is can we get something that acts like a maximum and minimum but isn't actually required to be part of the set? Because then that would actually solve this issue, right? And so to work towards this, let's see what happens if we remove the condition of being in the set. So what we get is something called upper bounds and lower bounds. The definition of an upper bound states that a subset A of the real numbers is bounded above if there exists a real number u such that u is bigger than or equal to everything in A. And this number u is actually called an upper bound for u. It's always helpful to compare and contrast definitions. Our brains learn better when we build connections. So notice the only difference between an upper bound and a maximum is that the upper bound does not actually have to be a part of the set, right? It only has condition 2 of the maximum, which is that it's bigger than or equal to everything in the set. And so as a result, this is a very loose condition, and we can find many upper bounds. Some are actually very poor upper bounds for a set. So let's take a look at an example. Let's say we have the number line and we have a set A whose elements are denoted in orange here. And you can see the elements in blue here are all candidates for upper bounds. These all satisfy the definition above because they're all bigger than or equal to all the orange elements. Whereas this red element here cannot be an upper bound because it's not bigger than or equal to, for example, these elements here. And so what we see is that with an upper bound, we could have a pretty good upper bound if it happens to be this one, or we could have a pretty bad upper bound if it's way off to the right over here. Similarly, the definition of a lower bound states a subset of the real numbers, let's call it A, is bounded below if there exists a real number, let's call it L, so that L is actually smaller than or equal to everything in my set A. And this number L that you see here we call a lower bound for A. So again, if I have my set A whose members are denoted in orange here, then all the elements here in blue are lower bounds because they're all less than or equal to everything inside of A. And the element here in red cannot be a lower bound because it's not smaller than or equal to everything inside of A. For example, these orange elements are actually strictly smaller than this red element. And so in summary, we can see that upper and lower bounds are similar to maximum and minimum, but they don't actually have to be elements of the set. And as a result, upper and lower bounds can be actually very loose estimates or not very tight. And so now the question is, how can we fix this issue of bad estimates while still allowing bounds that aren't in the set? For example, among all these upper bounds, I want to pick the best upper bound, right? In this case, the best upper bound would actually be the least upper bound here, right? The smallest upper bound in this case is actually the best upper bound. This is the tightest bound on my set, the most accurate bound on my set. Similarly, for lower bounds, I have so many options for lower bounds, but I hope you would agree that the best lower bound or the most accurate lower bound is actually the greatest lower bound. Now let's take a look at the definitions which precisely capture what we just talked about. Starting off with the definition of the supremum, a real number u is the least upper bound for a subset of real numbers if u is an upper bound for A, and if u naught is any upper bound for A, then u must be less than or equal to u naught. So you see how the supremum is an upper bound for the set A, and if u naught happens to be any other upper bound for A, then the supremum is always less than or equal to u naught. It's the least among all upper bounds, which is the best or the tightest upper bound. And the notation we use is actually the supremum of A. Similarly, the definition of the infimum states a real number L is the greatest lower bound for a subset of real numbers if L is a lower bound for A, and if L naught happens to be any lower bound for A, then L should be greater than or equal to L naught. So you see how the infimum is not just a lower bound, it's actually the greatest lower bound. It's bigger than or equal to any other lower bound you can find for A. And in this case, we use the notation INF, the infimum of A. Now there's a couple things to note here. The first is that the supremum and the infimum are unique when they exist. And the reason for this is by condition 2. Let's show the supremum is unique when it exists. To do this, let's suppose that S1 and S2 are two supremums of a set A. Well, since S1 is a supremum, it satisfies this definition. we have that S1 is less than or equal to any upper bound. In particular, it should be less than or equal to S2 because S2 is an upper bound for A, right? Similarly, S2 also satisfies this condition. That is, S2 is less than or equal to any upper bound. Well, do we know another upper bound? Yes, S1 is also an upper bound for A. So we get that S2 is less than or equal to S1. Well, if S1 is less than or equal to S2 and S2 is less than or equal to S1, then it must be the case that S1 equals S2, proving that the supremum of A is indeed unique. Can you maybe pause the video and convince yourself why the infimum must be unique using similar reasoning? It would be very beneficial to you. The next thing to note is that when a set has a maximum, then the supremum not only exists, but it actually equals the maximum. Similarly, if a set has a minimum, then the infimum not only exists, but is exactly equal to the minimum of A. Let me give you a sketch of the proof for the maximum and supremum case. So for this proof, we actually have to show two things. The first one is that the supremum of A exists, and second, that the supremum is exactly equal to the maximum. Now, we don't currently have the tools to show why the maximum of A exists, but it's very easy to show once we unlock the axiom of completeness. So for that reason, let's suppose that the supremum already exists. Let's suppose that we've already shown that. Now, how can we show that the supremum of A is exactly equal to the maximum of A? Well, we just have to work with this definition. We need to show that this number, this maximum of A number, satisfies these two properties, that it should be an upper bound for A, and if U0 is any other upper bound for A, well, then the maximum of A should be less than or equal to U0. Well, the maximum of A is an upper bound for A by definition. And for the second condition, if B is any upper bound, then by definition, it means that B is greater than or equal to everything in A. In particular, B must be greater than or equal to the maximum of A because the maximum is an element of A. And this shows the second condition, that the maximum of A is less than or equal to any upper bound B. Therefore, the supremum of A is exactly equal to the maximum of A. Next, I would like to revisit the examples that we already saw, but now in terms of the context of infimum and supremum. So for the first example, we had the finite set that contains 1, 10, 100, and 1000. And we saw that the minimum of this set was 1 and the maximum of the set was 1000. Well, using what we just talked about, since the minimum and maximum exist, both the infimum and supremum must exist, and they must equal the minimum and maximum respectively. For the second example, where we have the interval from 2 to infinity, we saw that the minimum of A is 2, and so therefore the infimum of A must also exist and must also equal 2. And in this case, both the maximum of A and the supremum of A do not exist because this set has no upper bound. And so therefore, it cannot have a least upper bound. For the next example, we have the set 1, 1/2, 1/3, 1/4, and so on. And in this case, the supremum is equal to the maximum, which are both 1. And we saw that the minimum of this set does not exist because the numbers get arbitrarily close to 0, but never actually equal 0. But in this case, the infimum of this set does exist and is exactly equal to 0. And so let's see how we can prove that the infimum of A is equal to 0. The first thing we need to show is that 0 is a lower bound. Well, if A happens to be some member of this set, then it has the following form. It's equal to 1 over n for some natural number n. And we know that 1 over n is always positive. It's always positive. And so this clearly shows that 0 is indeed a lower bound. Now let's show the second condition. Let L be a lower bound for A, and what we want to show is that 0 is actually the greatest lower bound, right? That is, 0 must be greater than or equal to this lower bound, L. In order to prove this, we will actually suppose not. Suppose that actually L is greater than 0. That is, L is actually a better lower bound. And now we will use a property that we haven't covered yet, but we will soon cover, and it's something called the Archimedean property. However, this property is actually quite intuitive. It says that the set of natural numbers is actually unbounded from above. That is, the set of natural numbers just keep increasing and increasing forever, which I hope you think is quite intuitive. But don't worry, we will cover this very soon. But assuming this property, then we know that there must exist a natural number, let's call it n naught, larger than 1 over L. So you see, L is some positive number. It might be very tiny, in which case 1 over L will be very large. But regardless, there should be a natural number strictly larger than this real number. And the Archimedean property will guarantee us this. And now just rearranging this inequality to solve for L here, what we see is that 1 over n naught is an element of A here, because all the members of A are of the form 1 over n for some natural number, and this is 1 over n naught, where n naught is a natural number. So most definitely this belongs in A. But not only does this belong in A, but it also has a property that it is strictly smaller than L. And this implies that L cannot be a lower bound, because we found an element that is actually smaller than L. And so this is a contradiction, and this contradiction arose because we suppose that L is greater than 0. And so therefore it must be the case that L is actually less than or equal to 0, and that proves the second part of the condition of the infimum. And therefore the infimum of this set is indeed 0. For the next example, let's consider the closed interval from 0 to 1. And we saw both the minimum and maximum exist, and so therefore both the infimum and supremum exist, and they're equal to the minimum and maximum. And for our last example, we just slightly modify the previous example so that instead we have an open interval from 0 to 1. And in this case, both the minimum and maximum do not exist, but it turns out that both the infimum and the supremum both exist. They're equal to 0 and 1 respectively. And let's do a quick proof of why the supremum of A in this case is 1. And again, we have to just work with the definition and show the two conditions. Let's begin by showing that 1 is indeed an upper bound for A. So if A is some element of my interval from 0 to 1, well then it must be the case that A is less than 1. And so from which we get that 1 is an upper bound, because what we have shown is that for any arbitrary element of this interval, 1 is greater than or equal to A. Next, let's let U be an upper bound for A, and what we want to show is that 1 is actually the least upper bound. That is, 1 is less than or equal to this new upper bound U. And so again, we will argue via contradiction. Let's suppose for contradiction that this new upper bound that we have is actually smaller than 1. And now we're going to construct a new number x that's actually a part of my set, my interval from 0 to 1, but it's actually larger than U. And that will actually contradict the fact that U was an upper bound. And I won't go through all the careful details again because we actually did a very similar proof in the first half of this video. But the idea is that we can actually squeeze a number between U and 1. We can easily take the midpoint of U and 1, or the average. So U plus 1 divided by 2, define that to be your x. Then you can check that x does indeed lie within the open interval from 0 to 1. And moreover, this x is strictly larger than U. And so this implies that U cannot be an upper bound for A, because we just constructed an element in our set strictly larger than it. And so this is a contradiction, which means that U is not less than 1, but that U is greater than or equal to 1. And this actually shows that 1 is indeed the least upper bound, which completes the proof that the supremum of A is equal to 1. Another thing I would like to mention here is that we saw that when the maximum and minimum exist, then both the supremum and infimum exist, and they're equal to the maximum and minimum. However, if the supremum or infimum exist, then that does not necessarily guarantee that the maximum or the minimum exist. They may or may not exist. Let's finish this video off by proving the following lemma, which is a very nice characterization of the supremum. Let A be a set of real numbers, and suppose S is an upper bound for A. Then this upper bound, S, is actually the supremum of A if and only if, for all epsilon greater than 0, there exists an element from A so that S minus epsilon is strictly less than A. So I know this looks a little bit complicated, but let's actually understand what this statement is saying. This statement is saying that an upper bound S is the least upper bound if and only if every number smaller than S is no longer an upper bound. What this statement is capturing is that if S is indeed the supremum, right, the least upper bound, then if I just subtract even a tiny amount from it, then it will no longer be an upper bound. And so there will always exist some element from A that is strictly larger than this, which means it's not an upper bound. And so this must hold for any epsilon greater than 0, no matter how small this positive number is. S minus epsilon should no longer be an upper bound for my set. Now what I said in words makes it sound obvious why this statement should be true, but let's actually prove a little bit more carefully by looking at both directions. So for the first direction, let's assume that we're given some upper bound, but this upper bound happens to be the supremum of A. It actually happens to be the least upper bound for A. And then now what we have to show is this second statement. And the second statement must hold for any epsilon greater than 0. So for that, we can let epsilon greater than 0 be given or be arbitrary. And then let's consider S minus epsilon. Well, if I do S minus epsilon, that must be strictly less than S. We know that S here is the least upper bound, right? That's given to us. S is the least upper bound. Well, if it's the least upper bound, then S minus epsilon can no longer be an upper bound. Because if it was, well then S cannot be the least upper bound, right? Because this would be a strictly smaller upper bound. And so since S minus epsilon is not an upper bound, what does that mean? Well, that means that there must exist an element from my set A that is strictly larger than S minus epsilon. In other words, S minus epsilon is not an upper bound because there are members of my set strictly larger than it. And so it's that simple. It just follows from the definition of the supremum, right? S is the least upper bound. And S minus epsilon is a number that is strictly smaller than S. So therefore, this cannot be an upper bound, because if it was an upper bound, well then we have a strictly smaller upper bound than our supremum, which is a contradiction. And so therefore, S minus epsilon cannot be an upper bound. And then what does it mean to not be an upper bound? That means there must be some member of my set that is strictly larger than S minus epsilon, and that completes the forward direction. Now let's show the other direction. That is, let's assume that we are given S, which happens to be an upper bound for A, and this upper bound A has the special property that for every epsilon greater than 0, there exists an A from my set so that A is larger than S minus epsilon. And what we want to show is that this S is actually the supremum of A. Now, how do we show that something is the supremum of A? Remember, we have to show two things. The first thing we need to show is that S is an upper bound for A. And number two, we have to show that it's the least upper bound. Well, we're already given that S is an upper bound for A, so that checks condition 1. So the only thing we need to check is condition 2. So for that, let B be an upper bound for A. And what I want to show is that S is the least upper bound. S is smaller than or equal to this upper bound B. And the way I like to do these type of proofs is actually by contradiction. Let's suppose for contradiction that actually B is strictly smaller than S. So now in order to proceed with this proof, we need to somehow apply this property. And in order to apply this property, we need a candidate for the epsilon. And looking at this inequality, since B is less than A, I can consider S minus B, which is positive, and try that as my epsilon. Well then, by assumption, there must exist an element A from my set so that S minus epsilon, and if you plug in for epsilon how we defined it here, simplifies very nicely to just B. And so what we get here is that B is strictly less than some element in our set A. Well, B is supposed to be an upper bound, right? B is supposed to be something that is bigger than or equal to everything in my set, capital A. But over here, we just found an element in our set, little a, that is actually strictly larger than B. And so this is a contradiction, right? This means that B is actually not an upper bound for A. And so this contradiction arose because of this assumption that B is strictly less than S. And so therefore, it must be the case that S is actually less than or equal to B, which is exactly what we wanted to show. And so therefore, S is indeed the supremum of A, completing the other direction. A similar type of result can actually be rephrased in terms of the infimum and lower bounds, which can be stated as, given that L is a lower bound for a set, L is actually going to be the greatest lower bound if and only if any number greater than L is not a lower bound. And so what I would highly encourage you to do is actually try this problem. Try to formulate this statement more mathematically as the previous result, and then go ahead and carefully prove both directions. It will really benefit your understanding and make sure that you really understand the definition of the infimum in this case. And that brings us to the end of this video, where we introduced the idea of the supremum and the infimum, which are like maximums and minimums, or they're like really tight upper or lower bounds. In the next video, we will finally cover the axiom of completeness. This is the crucial property that truly sets the set of real numbers apart from the set of rational numbers. Thanks for watching. If you enjoyed this video or found it helpful, I would really appreciate it if you could like the video and subscribe for more content. And if you have any questions or thoughts, feel free to leave a comment down below. I would love to hear from you.